In a way, I've been misleading you. The first examples and convergence theory we've seen so far have indicated that GMRES works really well. It turns out in real-world applications, the situation is not as nice. In real-world applications, your eigenvalue can be distributed in a very unfavorable way. For example, it can be distributed like this, so in a circle, and so GMRES will converge very slowly for this case. And you can even have examples where GMRES doesn't converge in a practical sense at all. We're going to be able to improve the set of applicable problems for GMRES by doing what we call preconditioning, which is in this context is just it's a transformation of the problem to a form which is more favorable for GMRES. So we start with the concept of left preconditioning, which corresponds to taking your linear system and multiplying from the left with a matrix M inverse, which we call M the preconditioner. So now we have a new linear system, Bx is equal to C, containing this M inverse matrix. And so we have effectively transformed the problem. And the idea of this left preconditioning is that you effectively apply GMRES to this transformed problem. So I said effectively apply GMRES because we are not explicitly going to compute the B matrix. We're only going to compute the action of the B matrix onto some vector. So we're going to have here, wherever we have a matrix vector product, we will instead replace it by M inverse AZ. So here is some MATLAB code, and you can see here that, okay, so wherever we had the B vector, we need to replace it by C, which is M inverse B. So we need one backslash operation here. And here we have W is equal to, so here we have a matrix vector product, and wherever we have a matrix product, we will instead replace it by this. So which doesn't explicitly require the computation of the matrix B, but it is equivalent to applying GMRES to this transform problem. Okay, so how do we build a good preconditioner? So we need these two properties in order to have a good preconditioner. So we want our linear system to converge, so GMRES for the linear system to converge faster than the original problem. So ideally, we should have that GMRES to this transform problem converges faster. And okay, since we have this additional cost to compute M inverse for its action, the action of this operator has to be fast as well. Let's look at two extreme situations and try to find the balancing between these two. Okay, so let's first just take M equal to the identity matrix. Okay, this doesn't actually transform the problem, so the transform problem is just equal to the original problem. And it will typically be have slow convergence, but so nice thing is that you have the application of the preconditioner is doesn't cost anything. So we have a super cheap preconditioner, but slow convergence. Okay, the second idealized situation here, or extreme situation, is when we select m is equal to a, and so then the transform problem is just identity x is equal to m inverse b. Okay, so it's again somehow trivial that x is equal to m inverse b, but in this context, we're gonna look at this as the situation where you apply GMRES to this problem. Okay, then you have fast convergence. Well, in fact, you have convergence in one step, since all the eigenvalues are identical, and GMRES converges if all eigenvalues are identical. But the downside is that the m inverse Z, so the action is very expensive. In fact, it's as expensive as the original problem. So nothing is gained. What we're gonna try, the philosophy of designing a preconditioner is a balancing between these two extreme situations. So we want a preconditioner typically which has is essentially an approximation of A, because then we will hopefully have fast convergence, and but we also want this to be cheap. And so now we look at some of the most common choices of these choices of M. Okay, first common choice is that we just select M equal to the diagonal elements of A. So we neglect all the off-diagonal elements. And this works really well if your off-diagonal elements are small. So matrices which are diagonally dominant will be well approximated in this situation. And the action is cheap to compute because M inverse times a vector is just, well, it's just this. Okay, and then you have this triangular-based preconditioner where you just, in a similar way to the diagonal, you can just take the upper triangular part or lower triangular part, and then you can do a linear solve, or M inverse times a vector using forward and backward substitution. More advanced examples include doing something like an LU decomposition, but doing approximations along the way, so you get an incomplete LU factorization. So an approximation of M that's approximated by L times U, or algebraic or geometric multigrid. So in the most advanced cases, these tend to work quite well for many real-world problems.